Welcome to your first video. This one's going to be on chemistry review, but before we get started, just a quick note. These are both for homework, but they're also study resources for you. If you find that you're struggling or finding a concept difficult to learn, then you can always come back to these videos and review them again and watch them as many times as you'd like to. So now back to chemistry. Our agenda for today, we're going to be going over some basic vocabulary, elements, compounds, atoms, molecules, isotope, and ions. We'll look at some basic patterns in the periodic table, and lastly, we'll go over 3 different ways to visually represent atoms and bonds. This is important because you'll come across all 3. It's important that you be able to read and interpret each. So the first thing, elements and compounds. Elements are substances that have only one type of atom. So the example that I have here for you guys to look at is gold, which is known as Au. So gold is entirely made up of gold atoms. It is only one type of atom, and it can exist because it's large and stable enough on its own in nature. For a lot of other elements, this won't be true. It needs to bond up with something else, or else it's unstable. The example we have of a compound right here is water, something you all are very familiar with. Now, the definition of a compound is that it's a chemical combination of 2 or more different elements in set proportions. So different becomes really important here because when we talk about molecules, I'll point it out again. The set proportions, what that means is that with water, the subscript here tells me that I need to have 2 hydrogens for every 1 oxygen. The 1 here is invisible, we don't write it in, but there is a 1 there. If I were to change those proportions, let's say I change this into H3O, I now have the hydronium ion, which is not the same as water. Or let's say I take a hydrogen away. I now have hydroxide, which again is not water. So the set proportions are like the fingerprint or the identity of the compound. You mess with the proportions and you've changed the compound. Next we have atoms and molecules. Atoms are the basic unit of an element. So the example I have for you here is oxygen. Oops, went the wrong way. So oxygen is an example of an atom. So see, we just have 1 by itself here. It gives me the number of protons and the number of neutrons in the center. Then over here, molecules, it's 2 or more atoms combined. See how in the definition it doesn't say 2 or more different atoms combined? That's because you can still have a molecule that is the same atom combined, such as with our diatomic elements. Diatomic elements, which oxygen is one of them, are a group of elements that do not like to be by themselves. They would prefer to bond up and have a buddy. It makes them more stable. So oxygen we see here forming a double bond with another oxygen. So this is still a molecule even though it's 2 of the same atom combined. We can also have molecules where it's different. So here we have carbon dioxide. The C is for the carbon, the O is for oxygen. So we have 2 different atoms combined and we see those definite proportions again. 1 carbon for every 2 oxygen. Both are molecules. And the last section for our chemistry vocabulary are isotopes and ions. Isotopes are atoms with a different number of neutrons. Atoms with a different number of electrons are called ions. So here we have neutrons for isotopes, electrons for ions. We only change the number of electrons for ions because if we were to change protons, we wouldn't get a different charge, we would get a different element entirely because the identity of an element is determined by the number of protons in its nucleus. So my example for isotopes we have right here is carbon. So here's carbon 12. We get the 12 because there's 6 protons, which is the fingerprint, so there's always 6 protons for carbon, and we have 6 neutrons. That's where the 12 comes from. This is the most common form of carbon. But we also have carbon 13, which is when we have 6 protons and we have 7 neutrons. And then finally we have carbon 14, which is 6 protons and 8 neutrons. Carbon 14 you'll hear about again when we do radioactive dating. Carbon 14 is a radioactive element. What that means is that with all those neutrons stuffed into the nucleus, it is not stable, which means that it gives off radioactive energy. We can measure that and study the decay of carbon 14, which is how we're able to date things that are very old. Now we have the periodic table. You do not need to know most of this. sections that we'll be most concerned with in this class are going to be your two ends, which is over here and over here. In the middle, you have your transition metals, which are shown in this light reddish color right there. Transition metals are not something we'll be discussing heavily. You still have iron, you have copper, we talked about gold earlier. So there are definitely ones that will be familiar to you, but they're not the focus really of this unit. So some good things to know about the periodic table. All of the rows that you have here going across are called periods. And the columns are called groups. Here, I'm just going to erase some of the marks I made so I can do some more writing. The group is important because if we skip our transition metals, which I just erased unfortunately, if we skip our transition metals, the group number will tell us how many valence shell electrons an element should have. So those are how many electrons are going to be in the outermost shell. So starting over here, it's 1, 2, skip the whole middle section, 3, 4, 5, 6, 7, and finally we come to our noble gases, 8. 8 is the number everybody wants. So the noble gases, think of noble, kind of snobby. They don't want to hang out with anyone or react because they already have all of their 8 valence shell electrons. They're happy and they'll kind of do their own thing. They're not really concerned about anybody else. The first type of model we'll be talking about is the Bohr model. The Bohr model is named after Niels Bohr, who was a very famous Danish physicist who was born in 1885 and died in 1962. He won the Nobel Prize in 1962. A lot of his work was in quantum physics, which is dealing with subatomic particles, sort of thing that they build the Large Hadron Collider to look at. Bohr had the unfortunate luck to be a Jew during World War II. So he actually had to flee his home country and he spent a brief amount of time in England before eventually coming to the United States. He was able to return home after the war was over though. So to create a Bohr model, the first step is to determine how many protons and electrons, and we can do that by looking at the atomic number on the periodic table. Then to find the atomic mass, you're going to subtract the number of protons from the atomic mass to calculate the number of neutrons. So we're going to look at magnesium right now, atomic number 12, and then I see that the atomic mass is 24.31. I'm going to round that to 24, round down, subtract the number of protons, and I get 12 neutrons. So now I know that I should have 12 electrons, 12 protons, and 12 neutrons. So on the next slide, I'm going to draw my magnesium. Alright, so I've started by creating my nucleus, which I sort of colored in a little yellow so you didn't get the line that I drew for the outside of my nucleus confused with an orbital. And inside my nucleus I've written the number of protons, which is 12, so 12p for protons, and 12n, n for neutrons. And so now what I need to do is go in and draw my electrons. So I know I need 12 electrons. And my first orbital gets 2. So I do 1 up top and 1 bottom. And that is the first electron shell. It just gets 2 electrons. Now I'm going all the way up to 12, so I'll write that up here so we can kind of keep track. Now my next orbital gets 8 electrons. So I start top, right, bottom, left, top, right, bottom, left. Now electrons are kind of like people getting on the bus. They prefer to sit by themselves before they're going to double up. So that's why I drew 1 on each location before I went back around and drew another one. So now I'm at 10, so I just need 2 more. So my last orbital, which will also get 8 electrons, I do 1, 2. 8 electrons for my last shell. And as you can see, obviously I'm missing a lot of other electrons, so this element would bond and react, but we will get to that in the next video. And that is a Bohr model. Next we have Lewis dot structures. Lewis dot structures are named after Gilbert Lewis. Gilbert Lewis is actually a Massachusetts native. He's from Weymouth. or was from Weymouth. He died in 1946. He attended Harvard University and had an extremely prestigious career. He had large discoveries in photons, phosphorescence, heavy water, and including creating the Lewis dot structures. He actually had sort of a sad end. Lewis was nominated 35 times for the Nobel Prize, but he didn't win a single one. And his death was sort of under suspicious circumstances. He had gone out to lunch with a man named Langmuir, who had recently won the Nobel Prize, and Gilbert Lewis and Langmuir had kind of been in a little bit of a friendly rivalry. So he came back to his lab and was found a little while later with open cyanide near him, which he had been working with, and he was dead. His death was ruled a heart attack, although it was never investigated, and it's believed by many that he actually killed himself. So Lewis contributed tremendously, though, to the field of chemistry, and one of his many contributions is the Lewis dot structure. It's less involved than the Bohr model, and you simply write the element symbol in the center, so the letters that represent it, and then you just write the valence shell electrons. So remember, valence shell are the electrons that are going to be on the outermost orbital. So right here we have the Lewis dot for magnesium. So when we drew it before, you guys saw that magnesium had 2 in its outermost shell. So here we have magnesium. It's got its chemical symbol and then 2 dots for those outer shell electrons, and that is it. So here, structure formula, I kind of gave you a little bit of a comparison so you could see the difference between it. Here's a Lewis dot for carbon dioxide, CO2. So see how they have each of these pairs of electrons right here represents shared electron pair. And then we have the extra ones. So if you notice, oxygen 1, 2, 3, 4, 5, 6, 7, 8, that's a happy oxygen. Same thing on this side, 1, 2, 3, 4, 5, 6, 7, 8. And then carbon is sharing 4 here, and it's sharing 4 here, which gives carbon 8 as well. So they have all gotten the 8 electrons they want, and they're happy. But instead of drawing all these dots, you can get even simpler by doing a structural formula. So all you do for a structural formula is where there is a sharing of electrons, you draw a line. So instead of drawing these 2 shared and the 2 shared here, it's just 2 lines. And you don't have to draw any of the electrons with a structural formula. Go back. There we go. So our wrap up. We reviewed basic chemistry vocabulary, learned about some of the important patterns in the periodic table, and reviewed 3 ways to represent atoms and molecules: Bohr models, Lewis dot, and structural formulas. So you should be able to do all of those things, hopefully. The ones we will use most in class will be the Lewis dot and the structural formulas. If you have any questions about anything in this video, should mostly have been review, hopefully, please email me and let me know.